my name is Justin Kruger. Today I am presenting on angles-only tracking and navigation for approach and rendezvous in geosynchronous orbits on behalf of my co-authors in the Stanford Space Rendezvous Laboratory and 10-1 Aerospace. I'll start off by talking about the motivation behind this problem. I'll then go through the navigation, architecture, and algorithms that we're applying at a fairly high level. And I'll then finish off by talking about three geostationary simulation scenarios. So the core goal of this is to enable the inspection, refueling, and servicing of resident space objects in GEO, because increased usage of space requires us to be much more efficient in how we leverage and maintain satellite resources. And GEO satellites are particularly attractive for this because they're often very large and expensive and fulfill critical long-term objectives. So we have, of course, challenges to overcome, such as navigation. How do we robustly characterize relevant targets in GEO and actually estimate their target relative orbits during the approach of a servicer vehicle, because targets might be uncooperative, they might be unknown, and any reliance on things like ground support or external sources such as GPS reduces our autonomy. So a possible solution then is optical angles-only navigation, as pictured on the right, where we have cameras on observers in the system, which measure the bearing angles to other target objects. And navigation then becomes autonomous and self-contained, but we face challenges also due to things like weaker state observability, because bearing angles don't give us a direct range measurement, as well as optical visibility constraints. Now, a particularly interesting upcoming flight demonstration of angles-only navigation is called StarFox, which will attempt to perform distributed autonomous angles-only navigation for 4 satellites in low Earth orbit. And this has been developed by the Stanford Space Rendezvous Laboratory for the NASA Starling mission. And for navigation, it applies something called Artemis, or the Absolute and Relative Trajectory Measurement System. Now, the question is, what if we wanted to apply Artemis to perform navigation in GEO? This actually presents a lot of new difficulties as well. For example, how do we discriminate between multiple very dynamically similar target objects in the GEO belt? How do we maintain tracking during fast approach maneuvers and long duration continuous maneuvers? How can we potentially have to leverage very highly uncertain a priori state information? And how do we deal with things like solar radiation pressure and the effects on our dynamics? So really the objective of this research has been to extend and modify Artemis to support satellite servicing applications in GEO and to then demonstrate it on some relevant simulation cases. So what does the Artemis architecture actually look like in itself? It's essentially a software payload deployed on a team of observer satellites, with 4 keywords being that it is angles only. It is also cooperative, so its observers can share measurements over a crosslink radio. It's distributed, so certain observers might only estimate a subset of target states. And it is basically autonomous. It requires minimal external state knowledge and ground interaction. So in the top left here is kind of a schematic of a 4 spacecraft Artemis system with 2 observers and 2 targets. Each observer is estimating its own 6 absolute orbit elements, as well as the 6 relative orbit elements, or ROE, of its targets, and optional state components such as sensor biases or clock biases as well. And on the right, we have the measurements. We get 2 bearing angles per target, as well as potentially bearing angles broadcast from remote observers of the same targets. Now, notably, Artemis leverages new algorithms to overcome some of the key limitations of previous flight demonstrations of angles-only navigation. So first, it is scalable to multiple observers and targets. It is able to resolve target range, which is weakly observable, without actually requiring any maneuvers. Via measurement sharing and cooperation, it can actually maintain an absolute orbit estimate as well, using only bearing angles, and can start navigation without requiring any a priori target state knowledge. So I'll now go a bit deeper into the 3 core Artemis algorithms, again at a pretty high level for time. So this is a block diagram showing the measurement sources for Artemis, as well as the 3 main software modules. So we have image processing, or IMP, in red, batch orbit determination, or BOD, in blue, and sequential orbit determination, or SOD, in green. And we also have 2 main stages of operation here. The first is an initialization step, where Artemis produces initial relative orbit estimates for each of its visible targets, and then a refinement step, where it refines the estimated states of the system using new measurements. So talking about IMP first, the goal here is to essentially produce batches of bearing angles for each visible target using a sequence of images from the onboard camera and a coarse estimate of the observer's absolute orbit at 1 epoch. And broadly, the way it does this is by two possible paths. So we start off on the left by computing the bearing angles to any unidentified objects in the field of view. And if we don't have any a priori target state info, we move along this top path where we use multi-hypothesis tracking to essentially enumerate all of the possible ways we can arrange unidentified objects into target tracks. And to actually assess them and pick which ones are physically reasonable, we apply kinematic models of target motion, since via orbit dynamics, we have an idea of how targets should move in the field of view of the camera. They should have, for example, this kind of elliptical shape here. And by applying these kinematic models to develop rules over time, we can robustly converge to the correct hypothesis. If we do have target state knowledge, we can actually use that to model where our expected measurements should be in the camera image and assign objects much more simply that way, in kind of single hypothesis tracking. Now, in GEO, we can have some issues here because consider the case when you have targets very close together in the field of view, or you have maneuvering targets kind of disrupting this motion model here. That means you can get very low assignment rates. Alternately, if your a priori information is very poor, then you can face errors when actually trying to match unidentified objects to target state estimates. So the way we've tried to increase the robustness of this in GEO is essentially combining these two paths and fusing the information sources together. So for example, if we have a maneuvering target or targets that are very close together and the kinematic modeling is poor, we use the state information to kind of bound the search space for multi-hypothesis tracking. And if the target state information is poor and potentially has a significant error, we apply the kinematic modeling over time to make sure the resulting tracks are still physically reasonable. So next is the BOD initialization module, where we perform initial relative orbit determination for our observer and targets using those bearing angle batches from image processing, and again, this coarse estimate of the observer absolute orbit at 1 epoch. So the existing BOD module applies this broad method where we separate the target state into strongly observable and weakly observable components, with the weakly observable part being the target range. And we generate essentially lots of samples for the range, and for each sample, we compute the corresponding state estimate using iterative batch least squares with our measurement batch. And our selected state initialization, as pictured here, is the one which produced the least measurement residuals. And we can also use those converged measurement residuals to estimate our initial state uncertainty. Now, the issue is that typical measurement collection periods for this method are 1 to 2 orbits, which is a long time, 1 or 2 days in GEO. And that limits our responsiveness. So we've explored an alternate method to do this using the polynomial mapping shown on the bottom left here, which maps the target relative position in the RTN frame, which is delta R, to delta alpha, which is the target ROE estimate, via this mapping in lowercase b and capital B. So essentially, that means given we have 3 bearing angle measurements, we can solve for an initial estimate for our ROE, potentially very quickly. Now, this method doesn't natively generate any kind of state uncertainty, which is important for robustness. So to actually generate some kind of uncertainty, we apply sampling techniques. So for example, if we have an idea of the noise parameters of the sensor, we can perform an uncentered transform, generate some sigma points to get an uncertainty. Or we could, for example, apply just pure Monte Carlo sampling around our received measurements to try and generate an uncertainty that way as well. Now, I won't actually have time to go into this part of the results in this presentation. You can see the paper for that. It turns out, actually, the broad conclusions are that performance of this method is very highly dependent on the noise of the sensor, given that we're relying on very few measurements, and also is affected quite significantly by the observability of the relative orbit by things like the size of the relative inclination vector between the observer and target. Finally, here we have the SOD module, where we have our initialized states, and now we want to refine them over time using new bearing angles from image processing and any bearing angles we might be receiving from other observers over the intersatellite link. So a couple of notes here on how this module operates. We apply an uncentered Kalman filter, a UKF, with fully nonlinear dynamics measurement models, which help preserve a lot of the higher order information that allows us to attain complete angles-only observability. And we also have this idea where we leverage measurements from multiple observers for essentially a kind of distributed stereo vision approach, which again vastly increases the observability of the system. A couple of other filter features as well. So we can exploit the filter structure and the filter orbit element state parametrization to very efficiently propagate dynamics on board, even with a UKF. And we can treat things like unmodeled dynamics via estimating empirical accelerations or adaptive process noise on board as well. Now, a couple of the GEO issues here are that originally we had applied a quasi-non-singular state representation. Now, this actually had a singularity near zero inclination, and a lot of GEO orbits are equatorial, so we have to deal with this somehow. And we also have solar radiation pressure. So solar radiation pressure can cause biases in our relative orbit element estimates, or even state divergence over long periods. And of course, we can try and model solar radiation pressure in a filter, but the ballistic coefficients of our targets might not be well known. So it's hard to do this robustly. So to try and solve this, we actually append the ballistic coefficients of our system objects to our state within the filter and estimate them online. And we move to a fully non-singular orbit parametrization. So now I'll finish off by going through three example simulation scenarios for GEO cases. So in the first scenario, one observer performs a fast approach towards a known target while also tracking two other targets in the field of view. You can see, I guess, the relative motion pictured on the right here in the radial, cross-track, and cross-track, long-track planes of the observer. We actually use our high-fidelity orbit propagation software, including all relevant perturbations. And we actually generate realistic image measurements using OpenGL software, including all of the relevant noise sources as well. One thing to note about this scenario is we assume quite coarse initial orbit knowledge of around 10 kilometers uncertainty in observer and target positions. So pretty rough initially. And here are actually some results from this, where we plot the state relative position errors and uncertainties in the RTN frame for our three targets. And you can see that despite that large initial position uncertainty, we can robustly establish tracking and actually maintain it throughout the maneuver period, which is shaded in gray here. Another thing to note is that the most of the error is in the weakly observable target range, as we probably expect, roughly a few hundred meters of error, which is actually on the order of 0.1% of the range here. So pretty good considering our ranges are on the order of several hundred kilometers in this kind of scenario. So here is a second example scenario, a little closer, slightly smaller ranges, where two observers actually cooperatively detect and track two completely unknown targets. So we actually don't know anything about these targets. We do the autonomous initialization on board using the BOD module. So here are some example results from this test, where we, again, on the bottom, we have the relative position errors. The top row here is actually the absolute position errors. And on the far right is the estimate of the differential ballistic coefficients. So I guess looking at the relative position errors here, we can see the observers can actually autonomously initialize navigation on board, which is very, very useful. You'll note, however, the initial range errors can be quite large on the order of 10 or 20 kilometers, which has to be taken into account. We actually can also maintain the absolute orbit estimates using our multi-observer cooperation, as shown in these top three plots. And as shown on the far right, we can also observe differential ballistic coefficients using only bearing angles for improved robustness and long-term autonomy as well. Now, the final scenario here is a refueling scenario. You'll see we're operating at much closer ranges in this figure on the right, where three targets approach and dock with a depot and refuel in sequence over a period of about 1 day. So here are some example results. You'll notice the state uncertainties are now on the order of meters to tens of meters throughout. We do see some spikes in the uncertainty when we execute maneuvers due to maneuver execution errors as modeled in our ground truth simulation. But over time, maneuvers do tend to aid observability because they help disambiguate the target range. And our state uncertainties are also a little bit proportional to target range because essentially the noise floor of the sensor is proportional to a larger geometric uncertainty at larger ranges. But importantly, we can actually use angles-only navigation to support these kinds of close-range operations, perhaps in concert with another sensor at very close ranges. So in summary, Artemis enables autonomous angles-only orbit determination for varying multi-agent scenarios. The algorithms have been extended here to allow operation in geostationary orbits and have been successfully applied to simulations of approach maneuvers, inspection, and rendezvous. There are, of course, many future research directions we are exploring. The most immediate is actually supporting Star Fox flight experiments to demonstrate Artemis in orbit, in low Earth orbit, as well as things like fusion of additional measurement sources, uncertainty-aware filtering for actually detecting and tracking unknown target maneuvers, as well as optimizing the observer attitude for consistent target visibility. Thank you for your attention. I'm happy to take any questions.